All right, welcome back, guys, to part 2 of our Calculus 1 final review. Now, in part 1, we did 16 problems discussing, we did limits, and we kind of did the beginning derivative stuff. We, talked about, we did a problem on chain rule, we did implicit differentiation, we did exponential growth and decay, and we did related rates. In this video, we're going to be doing some problems on applications of derivatives, and we will be talking about integration as well, because that does get covered for, I believe, most Calculus 1 classes. They cover up to U-substitution at the end of the class, so that's what we'll be going up to in this video. But let's take a closer look, and I have all the timestamps to the left here. But we're going to start out with doing some problems finding the min and max values for a certain graph. We're going to head on to mean value theorem. Okay, we have a problem there because I think that's often brought up on finals. And we're going to also be doing derivative graphs. And what I mean by derivative graphs is we're going to be, analyzing a function like f of x, right? We're going to be analyzing that function based on its derivatives, right? So its first derivative tells us, its critical point, its extrema, right? And then the second derivative tells us the concavity, okay? And the inflection points and all that, okay? So that's what we're going to be looking at with derivative graphs. Then going from there, we're going to talk about L'Hopital's rule, a nice way to evaluate limits that end in, in a 0 over 0 or infinity over infinity case when you plug in. We're going to be talking about optimization, which I think is the hardest part of Calculus 1 for most students. And then we're going to dive into some integration stuff. So we'll talk about the fundamental theorem of calculus. We'll talk about part 1 and part 2. So that kind of is definite integrals. Okay, so that fundamental theorem of calculus covers definite integration. Then we'll move on to indefinite integration, so integrals without bounds, right? And then we'll go on to U-substitutions. Before I begin, just to let you know, we have 14 problems to do in this video, so that'll total up to be 30 throughout both parts. And these problems are going to be, most of these problems are going to be of harder difficulty, just to make sure we can help you prepare for this test. Okay? So moving on to our first problem on mins and maxes. We want to find all extrema for the function f of x equals 2 cosine x plus sine of 2x on the interval from 0 to pi over 2. We want to label each extrema as a local max or min, or if it's absolute max or min, we got to do that too. Okay, so the first thing I'm going to do is just restate our function. So we have f of x equals 2 cosine x plus sine of 2x. Okay, and well, how do we find all the mins and maxes? Well, we take a derivative, okay? And we set that derivative equal to 0 because where the slope is 0, we have our critical points, right? We have our extrema. Now, keep in mind, though, it doesn't, and we'll focus on this later when we talk about sign charts, but, take, for example, the graph x cubed. At the x equals 0 point, right, the slope is 0, but that's not a min or a max. So that'll all come clear when we talk about sign charts. Okay, and we'll do that after we find what our critical points are. Now, our first derivative here is going to be negative 2 sine of x, right? And then we have to do chain rule on the sine of 2x, in which we would get 2 cosine of 2x, right? And if you're wondering where the 2 comes from, it's from the derivative of 2x, right? That's the chain rule. Okay? Now, we can set 0 equal to negative 2 sine x plus 2 cosine 2x. And then we can solve from here, and how we can do that is just adding 2 sine x over to the other side, in which case the 2's go away. All right, and we just end up getting sine x equals cosine of 2x. Okay, now here's where I think a lot of students would get stuck. And, there's a couple different ways to solve this here, okay? Now, when I first looked at this, I really wasn't sure exactly where to go because, I thought about, stop texting me, I thought about just solving by observation, right? Looking at this and going, okay, well, I can see here that, you do a little bit of guess and check, and you can see here that x would be pi over 6, or it'd be 30 degrees. But, is there an actual way to end up solving for x? And of course there is, but it's not something that you would think of in a derivative problem. You actually have to use a trig identity because it's a double angle of cosine, right? So using if you want to actually solve here and you don't want to solve this by observation, you just go, okay, well, I know that sine of 30 equals cosine of 60, right? So that x must be pi over 6, which, you know, is an acceptable way to solve this. But if you don't think that that's something you would be able to do, okay, or you just don't feel comfortable with that, we can just set sine x equal to the double angle for cosine. The one we're going to use is 1 minus 2 sine squared x. So we can rewrite this as 2 sine squared x plus sine x minus 1 equals 0. And from there we can perform the quadratic formula with sine of x, right? Because we have a quadratic with sine of x. So we perform the quadratic formula and we get what sine of x is equal to, right? So it's equal to negative b, which is negative 1 plus or minus the square root of b squared minus a 4ac, which will be plus 8. It'll be all over 2a, 2a being 4. Okay, so assuming that you now have that written down, because I don't want to go too fast here, you end up getting negative 1 plus or minus 3 over 4, right? And so you would get that sine x equals 1/2 and negative 1. Okay, when sine x, in what this means, you can tell is that x equals pi over 6, right? That's when sine x equals 1/2. And when sine x equals negative 1, it's equal to 3 pi over 2. Now, here's the problem though. And here's a big thing for mins and maxes, you know, they might give you an interval. And I think there's kind of like a 50-50 shot that they'll give you an interval. You need to keep that interval in mind. Remember, our interval is from 0 to pi over 2. So we don't need to worry about that critical point, 3 pi over 2. Right, that's not in our interval. Pi over 6 is. And also, when I was talking about solving it by observation, I didn't talk about, you know, because there was other solutions to that problem. It could have been other values of x that were in different quadrants, right? But I didn't talk about that because that was outside of our interval. Okay, so you got to always keep that interval in mind. So this 3 pi over 2 goes away, and the only critical point we need to analyze is at pi over 6. Now, this is where sign charts come into play, okay? And sign charts, what I'm basically talking about here, if you are kind of unfamiliar with sign charts, is we're going to kind of look at x values around pi over 6 and plug those into our first derivative. Our first derivative being right here. So I'll bring that down. And we're just going to see, okay, is the first derivative positive or negative, and that will tell us if pi over 6 is a max min or neither. Okay, and let's also keep in mind our interval here from 0 to pi over 2. Okay, so we know, where we're going up to. So let's pick a value less than pi over 6 and greater than or equal to 0, and I'll pick 0 for this. It'll be a nice number to work with. F prime of 0 equals negative 2 sine of 0 plus 2 cosine of 2 times 0, right? And this just ends up equaling 2. Okay? Although we need to know, it doesn't matter the exact value, but what does matter is the sign of the value. We know that 2 is a positive number, so from 0 to pi over 6, the slope is going to be positive. Now, how can I make that conclusion just from one point? Well, we already know there are critical points where the slope could possibly change over from positive to negative, in which case it must cross 0, right? Because this is a continuous function, okay? Or else we wouldn't be able to do the things that we're doing to it. So we understand that would make that whole entire interval from 0 to pi over 6 positive. Okay, there's no other place where it could possibly switch over to a negative. Okay, now let's pick a value in between pi over 6 and pi over 2. And actually, I'm just going to go out with pi over 2 here. And we'll plug that in and get negative 2 sine of pi over 2 plus a 2 cosine of 2 times pi over 2, which is just pi. As you can see here, we'll get two negative values. We'll get negative 2, and we'll get a 2 cosine pi is negative 2 as well. So we end up just getting negative 4. Okay, that's a negative value. And so what we have here is the slope going from positive to negative. Now, does that mean that it's a max or a min? Well, you can look at this and you know, just graph it, right? And it doesn't need to be the exact graph of the function. I'm just talking about the slope going from positive to negative. If you talk about a slope being positive, right, it's going up, and then if it's going negative, it's going down. So your critical point's right here, and well, that would be a max. Okay? Rather, if it went negative to positive, right, then this would be a min. And if it went positive to positive, like for x cubed, it would be neither. Okay? So that's the idea, right? This is positive to negative, this is negative to positive, and this is positive to positive, but the same graph flipped would just be negative, negative, which, you know, would also be neither. Okay, so we know that there is a max, right? And that would be an absolute max. And I'll talk about that in just a second here once I finish writing this down. We have an absolute max at f of pi over 6. I'm going to write it like this so I can include both the x and the y points, right? I just like writing it this way. We'll plug in pi over 6 to our original function to complete this. Okay, so actually I'll put this down here. Okay, and if we plug in pi over 6, we get 2 cosine of pi over 6 plus sine of 2 times pi over 6 is pi over 3. Okay, pi over 3 is just 60 degrees. So we get 2 times a rad 3 over 2 plus a rad 3 over 2, and we get 3 rad 3 over 2. Okay, so 3 rad 3 over 2. That is going to be our first extrema. Okay, that's our absolute max. But that's not it, right? We're not done. And the reason why we're not done is because there's minimums on this graph as well. Okay, now the reason for that being, we have our boundary, right, from 0 to pi over 2. So we're going to have a min both at 0 and at pi over 2 as well, right? Because remember that graph I drew where it's just kind of like a upside down parabola, right? Picture 0 and pi over 2 being at the ends of that, okay? And now, you know, you have to see, is 0 higher, is pi over 2 higher? So you're going to have local mins at both, but one is going to be an absolute min, okay? So we need to figure that out. Now, to do that, we'll plug in 0 first, and then we'll plug in pi over 2. So we have 2 cosine of 0 plus a sine of 0, right? 2 times 0 is 0. And from that, we get 2. Okay, so there's the value at f of 0. Now what about f of pi over 2? Well, that's going to be 2 cosine of pi over 2 plus sine of 2 pi, it would be 2 pi over 2, right? And we know that both of those end up being 0, so we get 0 there. Okay, so this would be a local min, and this would be absolute min. The reason why is because it's lower, right? It's lower, so that's the lowest point on your interval. Okay, the highest point on your interval, though, that would be the pi over 6 point, right? We know that's a max, and that's the only max on that interval, so that's the absolute max. Okay, so now we can just write this down. So we can write down that we have a absolute min at f of 0, nope, not f of 0, f of pi over 2 equals 0. And then we have a local min at f of 0 equals 2. Again, I like to write it in that notation just because now I get to include both the x and the y coordinates. Okay? I just think it's a really clean way of writing it. But yeah, so that's our answer for number 1. So now let's move on to our next problem, which is on mean value theorem. Okay, that is number 2. And it asks, if f of x equals the natural log of x from the interval 1 to 4, show that there is a number c that satisfies the conclusion of the mean value theorem. Now, this problem is going to be very, very hard if you don't know what the mean value theorem actually is, okay? And I definitely struggled with that too when I was in calculus. Like, I didn't know, I couldn't remember what the mean value theorem was. I believe that like happened to me once on like a test or something like that, because it was glossed over so quick, you know, like it was just this quick little thing that I don't think I fully understood, and or at least I didn't remember the formula too, you know. But it's actually a really easy theorem, and I'll explain that to you now. So basically, what the mean value theorem says is that f prime of c, right? So, and I'll explain what that is in a second, equals y2 minus y1 over x2 minus x1. And the reason why I said it like that is because this is basically the slope formula. Okay, for when you had a line or something like that, you had m equals y2 minus y1 over x2 minus x1, which can also be written as the change in y over change in x. Right? Well, basically what this f prime of c is it's m. Okay? This is m. Okay? What the mean value theorem is saying is that at some point from the interval a to b, okay, your slope, right, has to equal f prime of c, right? At some point c, your slope will have to be the same as if it were a line going from a straight line going from point 1 to point 2. Okay? The reason why it has to be that slope at some point is because if it was never as high as that slope, well, then you would never reach your second point, right? It would be lower than your second point. Okay, if your slope was never high enough. But if your slope was too high, right, if it never was small enough to be that f prime of c, then your point would be way too high, right? Then it would be higher than f prime of c, or sorry, than your second point. Okay, so actually, let me graph this so I can make sure that you get what I'm saying. Okay, so let's say that this is our x-axis. Okay, and this is our y, and we have point 1 here and point 2 here. Okay, if your slope never hit f prime of c because it was always lower than it, your point would end up down here. If it was always higher than f prime of c, your point would end up here. And if it skipped over f prime of c, right, then you probably have some kind of discontinuity or something like that. Okay, so it wouldn't, in which case we couldn't be taking derivatives and doing things like that. Okay, so that's the idea with the mean value theorem. Now we need to actually find that value c. So what we're going to do is use this formula. Okay, we get that f prime of c is equal to, so f of b, right? What is f of b? Well, it's natural log of 4, right? Because we have to plug in that 4 into our natural log of x function. So we get natural log of 4 minus f of a would be natural log of 1. And then b minus a is 4 minus 1. So we get the natural log of 4. Natural log of 1 is 0. So we just get the natural log of 4 over 3. Okay? Now what do we know that, like how we actually end up finishing this, right, and finding that number c, is we're going to have to take the derivative of the actual function f of x. Okay, so remember your derivative of a natural log. Okay, the derivative of natural log of x is 1 over x. Okay, so according to this derivative, f prime of c would be 1 over c. Okay, well, we know f prime over c in these two places. It's natural log of 4 over 3, and it's 1 over c. So we can just set these two things equal to each other, right? 1 over c equals natural log of 4 over 3. Okay? You can put both sides to the negative 1 power, which basically just means flipping them, and you get c is equal to 3 over the natural log of 4. And right there is your answer. Okay? So that's the idea with the mean value theorem. It's generally a very, very quick problem, but you just have to remember that formula. And remember, it's the same thing as your slope formula. Okay? It's the same exact thing. You find, if it's asking for c, you can find f prime of c with the mean value theorem. Find what f prime of c is if you just take the derivative of the function in general and then just plug in c wherever you see an x. Okay, and that's it. Okay, so that's what you would expect from a mean value theorem problem. Moving on to our third problem, we are going to be talking about derivative graphs. Okay, so for the function g of x equals x squared minus x minus the natural log of x, find the intervals on which g is increasing or decreasing, the local maximum and minimum values of g, and the intervals and concavity, intervals of concavity and the inflection point. Okay, so this is a lot of information they're throwing at you. Okay. So what we're going to do is I'm just going to group up this information. Okay, so they're asking for 3 things. Okay, I'll label this 1, 2, and 3. They're asking for intervals of increase and decrease. They're asking for the local max and min values. And they're asking for, we can just combine this thing, intervals of concavity and inflection points. Right, so that'll all be told from the second derivative. Okay, so let's just start off here, okay, and start off with number 1. Okay, we want to find the intervals of increasing and decreasing of this function. Okay, so we'll start off with g of x equals x squared minus x minus the natural log of x. Okay, and well, what we're going to do is take a derivative, right? Because we got to find out where this thing is increasing or decreasing. So it's just like our first problem, right? I could have told you where that thing was increasing and where it was decreasing based on taking the derivative, setting it equal to 0, and setting up a sign chart. It's exactly what we're going to be doing here. But instead of talking about where there's local and local max and mins and absolute max and mins, what we're going to be talking about is increasing and decreasing. And of course, then the step 2 is the local max and mins. So taking a derivative of this, we get 2x minus 1 over x. Okay? 2x minus 1 over x. Okay? And we set it equal to 0. 2x minus 1 over x. Okay? And from there, we can add 1 over x to each side. And from there, we can multiply x on each side. Okay, so we can actually say that this is 1 equal to 2x squared minus x. Okay, in which case we can now subtract the 1 over, and we have a quadratic. Okay, so now we got to get that quadratic formula done, and we get that x is equal to negative b, so it's equal to 1 plus or minus the square root of b squared, 1, plus, well, minus a 4ac, but since we have a negative here, this will be plus. 4ac is going to be 8, and then we have 2a, which is 4. Okay, so we kind of get something similar to the quadratic we had before, where we get 1 plus or minus 3 over 4. Okay, so what this means is that x equals 1 and x equals negative 1/2. Okay, so basically now we know that we have critical points, right? We have critical points at 1 and negative 1/2. So now we have to analyze these with a sign chart. Okay, and the sign chart's going to actually be a little easier this time because we don't have to worry about our interval at all. We don't really have an interval for this, okay? I mean, we do have the domain of the function, right? We know that the natural log of x, right? That makes it so we can't have any x that is 0 or less, right? So that actually cancels out one of our critical points. Okay, so and that's something you would see if you went through the problem and tried to use that negative 1/2 critical point. You would see that, hey, this doesn't work because you can't have the natural log of a negative number. Okay, so what ends up happening is you just analyze 1. Okay, and so I'll cross that out. So that's something to check, but anyways, let's get into actually analyzing our derivative. Okay, so we have, I don't know why I switched to yellow there. So we have f prime of x, or sorry, g prime of x, equals 2x minus 1 minus 1 over x. Okay, so you can even see right there, we couldn't have had a 0 there, and well, in this case we can't have a negative, but it's more obvious with our g of x function, right? That'll tell you the domain of the function you're dealing with. Let's plug in 1/2. Okay, we'll plug in 1/2 over here, and we'll plug in a 2 over here. So we have g prime of 1/2 equals 2 times 1/2 minus 1 over 1/2, which is 2. That gives us a 2 times 1/2 is 1 minus 1 minus 2. Okay, so we get 1 minus 1 is 0, minus 2 is negative 2. So we get a negative here. For 2, we just plug in 2. We get a 2 times 2 minus 1 over 2. And in that case, we get 4 minus 1 minus 1/2, and you can see that that's going to be positive. So we're going from a negative slope to a positive slope here. Okay, so we're dealing with a min, and that'll be something good to note for the next part of this problem. Okay, so from this data, okay, I'll call it data, okay, we can now talk about what's our increasing interval, what's our decreasing interval, okay? And we also still need to keep in mind that that we need to make sure we're accounting for our domain of our original function. Okay, so let's write increasing from, and we'll write decreasing from. Okay, we can see that it's going to be increasing from this point as 1, our min, and our function will go up until infinity, right? This thing, its domain is from 0 to infinity. Okay, so it's going to be increasing from 1 to infinity and decreasing from 0 to 1. Okay, and that is the answer to the first part of this problem. Moving on to part 2, we're going to talk a little bit about local max and mins again, all right? And we know from our first part that there is going to be a local min at x equals 1. Okay, we don't know though what the actual value of that is, and actually that's what the problem is asking for, right? It's asking for the values of the local maxes and mins. Okay, so if it's asking for the values, it wants the y points. All right, so all we have to do now is just plug in 1 to our function. Okay, and remember, our function is x squared minus x minus natural log of x. which gives us 1 minus 1 minus the natural log of 1. Natural log of 1 is 0, 1 minus 1 is 0, so we just get a big 0 here. So we can write we have a local min at g of 1 equals 0. Okay, and that is our second part. Actually, I'll circle the whole thing. Okay, and then we move on to our last part, right? And that's just checking for concavity and inflection points. So we got to take into account our g prime of x here, right? And just take a derivative of it. Remember, our second derivative tells us the inflection points, right, where it's equal to 0, what the second derivative is equal to 0, and it also tells us the concavity, right? So where the second derivative is positive, that's our positive concavity, right? So it's concave up, and then where it's the second derivative is negative, you have concave down. Okay, so you're talking about like an upside down parabola, right? That's what it kind of ends up looking like. All right, so let's take our derivative here. We get 2, and then the derivative of 1 over x is something that you should memorize because it shows up a lot. The derivative of 1 over x is negative 1 over x squared. So this ends up being plus 1 over x squared. Okay, so setting this equal to 0, we get 0 is equal to 2 plus 1 over x squared. This means that negative 2 is equal to 1 over x squared. And so we can write that as x squared equals negative 1/2. Okay, and you see here though that we'll end up getting imaginary points for when our second derivative is 0, right? Because we have a negative under the radical in that case. We square root both sides. So that means that we don't have any real inflection points. Okay, so we'll write no real inflection points. Okay, so I guess, maybe a side quest of this problem is to stump you with, okay, well, what happens when there's no real inflection points? Like, what do? You just, write down no real inflection points, right? That might confuse some students, so that's something those jerks would try to do. So what we want to do now, we have to still find concavity. We know it's going to be either concave up or concave down on the entire interval. So we're just going to plug in a point on that interval, right, on the domain of the function, and that's it. We just see, okay, is that positive or negative? So I'll plug in 1, since we've been using 1 a lot, since it's a critical point. And we get 2 plus 1 over 1, which is 3. And that's positive. So we know that it's concave up on the entire interval. And that is the last part of our problem, okay? So kind of going over what we did here, okay? We wanted to find the intervals of increase and decrease, okay? So we took a first derivative, set it equal to 0, did a sign chart, okay? And that's how we found out our interval, right? We also had to make sure that we analyze the domain of the function. That does usually become apparent. I assume it'll always be apparent while you're doing the problem if you have forgotten about the domain of the function, but that always is really, really important to look at, okay? Because if we would have included negative 1/2 as an actual critical point, we would have got the problem wrong, okay? So from that sign chart, we found out where this thing was increasing or decreasing, and from that sign chart, we also found out that we had a local min at x equals 1. We found the y point at x equals 1, and that became our answer. And for number 3, we took another derivative and set it equal to 0 to find our inflection points. We found that, since when we square root both sides here, we'll be taking the square root of a negative number, that there are no real inflection points. And so our concavity was either concave up or concave down. Here we know that it was concave up because we plugged in one of our x values that was on the interval. We found it to be positive. There we go. We have concave up. Moving on to problem number 4, we are asked to use the information that we found in the last problem to graph g of x equals x squared minus x minus the natural log of x. Okay, now honestly, don't freak out here, okay, because this is not that hard of a problem. You just need to accurately process all the information, all the answers, all right, that you had in the last problem. If you got all those right, then you'll get this problem right. Okay, it's not going to be that difficult, but I think when I was in Calc 1, I really thought that problems like this were insanely hard, and they actually ended up being pretty simple. Okay, so let's bring down all the information. Okay, first off, we have our increasing and decreasing. Okay, we'll bring that up here. We'll bring down that we have a local min. And where that is. Oops. Okay, we will talk about that we have, no real inflection points. Actually, we don't even need to include that. We can just talk about being concave up on the entire interval. Okay, so putting all those things together, first off, we can just list off a point. Okay, we have that at x equals 1, we have a point right here. Okay, and all this is saying is that it's first off going to be, it's kind of going to look like a regular parabola in a sense. That's what this is, right? It's increasing from 1 to infinity, so it's going to, it's not upside down, right? It's coming out of the point actually from your angle. This is probably the positive x direction, right? So it's going to look like that, and then since it's decreasing from 0 to 1, it's going to be coming from the other way, right? And remember that we have to take into account the domain of our function, so it's not going to touch the x equals 0 or any negatives. So what this function will end up looking like is like here and right here. Okay, so that is literally this function. That's all it is. For number 5, we're doing L'Hopital's rule. Okay, so find the limit as x approaches 1 of x over x minus 1 minus 1 over natural log of x. Now, what should kind of clue you in that this is L'Hopital's rule is that when you go through and do this, okay, when you plug in 1, you get 1 over 1 minus 1 minus a 1 over the natural log of 1, which is 0. Okay, so you end up getting a 1 over 0 minus 1 over 0. Okay, and that should make you think that maybe this is going to have an indeterminate form. The only thing is you have to find how to get to that indeterminate form so you know what form to take a derivative of the top and bottom of. Okay, but usually when we have a L'Hopital problem, we have a fraction, right? Just one fraction though. We don't have two fractions. That wouldn't make sense to take a derivative of the top and the bottom. So what we're going to do is combine these fractions. So we combine these fractions by just finding common denominators. We multiply this fraction by natural log of x over natural log of x. And we multiply this fraction by x minus 1 over x minus 1. So we just end up getting x times the natural log of x minus a x minus 1 over natural log of x times x minus 1. Okay, now what we can do is look at the limit as x approaches 1 of this quantity. Sorry, this is not what I wanted to put down there. What we want to put down there is this. Okay, now let's plug in 1 and see what we get, right? Well, we get a 1 times the natural log of 1, which is going to be 0, minus a 1 minus 1 over natural log of 1, which is 0, times 1 minus 1. This just gives us 0 over 0, so we know we have an indeterminate form. We can use L'Hopital's rule, okay? When we have a 0 over 0 case or an infinity over infinity case, we know we can use L'Hopital's rule. Okay, so we can take a derivative of the top of this limit, take a derivative of the bottom of this limit, and then we know that the evaluation of this limit will equal what it is right now, right? So the evaluation of the limit when we take the derivative of the top and bottom piece will equal the limit that we have now. That's L'Hopital's rule. So we take a derivative of the top. Taking a derivative of, remember, this piece right here. So we're taking a derivative of the top first, so x natural log of x minus 1. Okay, when we do that, we'll use product rule for the first part here. So this is just natural log of x plus we'll take a derivative of the natural log of x part now. So we would get an x over x, which is just 1. And then we would have minus x minus let's actually expand that out. If we take away these parentheses, we would get a minus x plus 1. So in this case, we get minus 1, and then the plus 1 goes away. Taking a derivative of the bottom now. Natural log of x times x minus 1. This is chain rule again, or this is product rule again. So we'll first have the derivative of x minus 1 is just 1, so we have that natural log of x by itself again. And then taking derivative of the natural log of x and multiplying it by x times x minus 1, we just get x minus 1 over x. Okay? So going on from there, first off, we can simplify this by just, since we have 2 terms in the numerator and 1 term in the denominator, we can rewrite this as the limit as x approaches 1 of natural log of x. First off, this is 0. So we get natural log of x plus an x over x minus 1 over x. Okay, that's a very helpful thing in calculus, to be able to have fractions like this and rewrite them like this. Okay, I've had some history with that, like having integrals, and I actually have one later where you have to do that. So keep that in mind, maybe. That's a little clue, but that is a huge deal to remember. I've gotten points off on plenty of tests because I didn't remember to do something as simple as that. Okay, but that's a story for another time. We can continue to simplify this as natural log of x over the natural log of x plus 1 minus 1 over x. Okay, so now let's see what this it ends up being now. Maybe it's better. Well, we get the natural log of 1 over natural log of 1 plus 1 minus 1, which gives us another 0 over 0 case. So now we got to use L'Hopital's rule again. It won't be as bad though, because taking a derivative of the top, okay, taking a derivative of the top, we know that's just 1 over x, and taking a derivative of the bottom, we know that's 1 over x, and then we'll have a plus 1 over x squared, right? And that plus 1 over x squared just comes from the negative 1 over x. The plus 1 goes away. So now, let's plug in 1 again, and hopefully something better happens. Okay, we plug in 1, we get 1 over 1 plus 1, which is 1/2. Okay, so there we go. The answer is 1/2. We had to use L'Hopital's rule twice, so it was pretty tedious, but we ended up actually getting an answer. Now, I don't think you would get any L'Hopital's rule problem that's any really harder than that on your final. But because you have other problems to do, right? You can't take forever on one problem. So they're not going to give you an insanely hard L'Hopital's rule problem, in my opinion. But you most likely will have to do 2 iterations of L'Hopital's rule. I think that's a very likely scenario for any test, because they want to throw in an extra trick or 2 in each problems, and there you go. You have to take L'Hopital's rule twice. So I'd be on the lookout for that. I think this problem is a great example of something that you would maybe see on your final. Here's a problem that's a little bit harder. Another L'Hopital's rule problem. We want to find the limit as x approaches infinity of 1 over 1 plus x all to the x power. Now this problem is very, very interesting, because if you look at this as x approaches infinity, if you have an infinite quantity on the bottom, right, this whole fraction ends up going to 0, right? You have 1 over a very, very, very large number. Okay, that's going to be a very, very, very small number. As you keep increasing that bottom number, that thing will go to 0. Okay, so you essentially end up just getting 1 to the infinity, right? You have a 1 plus 0 to the x approaches infinity, right? So you've infinity. Wouldn't you just get 1 over the infinity, which is 1, right? Wouldn't you get that? Well, in this case, no. And before you go raging and saying, no, 1 to the infinity is 1, I'll explain that, okay? But just know that for limits, 1 over the infinity is an indeterminate form. Okay, and I'll be able to prove that right now. Okay, 1 to the infinity is an indeterminate form. Now, the number 1, exactly 1, to the infinity, yes, I agree that that's 1. If you multiply 1 an infinite number of times, you're still going to get 1. But when we're talking about limits, we're talking about a number that is approaching 1. We're not talking about exactly 1, right? Now, the problem is that if you have any number less than 1, doesn't matter how close it is to 1, if you multiply that by itself an infinite number of times and it's smaller than 1, you get 0, okay? But if you have anything that's larger than 1 and you multiply by itself an infinite number of times, you get an infinitely large number, okay? So you don't have any continuity there, okay? It's either 0 or it's infinity, okay? And only exactly at 1, when you multiply 1 an infinite number of times, you get 1. So maybe you can kind of start to understand why this is an indeterminate form, okay? Because when you're talking, there's no continuity if you had something like that. It's either 0 or it's an infinity, right? So it's kind of like this huge jump, all right? So basically, this is an indeterminate form. So we want to use L'Hopital's rule, but we need to make this, we would have to end up making this a fraction, right? Let's say that L equals the limit as x approaches infinity of 1 over 1 plus x to the x, right? So now I can take a natural log of both sides and take the natural log of this limit. Now, the reason why I'm taking a natural log of both sides is to handle that power, that x and the exponent. If we get rid of that, this problem becomes a lot easier. Okay? So if we end up with the natural log of L is equal to, we can shove the natural log inside of the limit. Okay, we can shove pretty much anything we want inside that limit. Okay, so we get the limit as x approaches infinity. This x power can come down and be in front of the natural log. So we get x natural log of 1 over 1 plus x. So now all that's left to do to get this into something that we can do L'Hopital's rule on is to express x as 1 over x in the denominator. So we get this. Okay, this is still equal, right? But now we're expressing it a little bit differently, so we still get a 0 over 0 case. And you can see that if we use infinity here, we get the natural log of 1, which is 0 over 0. 1 to the infinity. 1 over infinity is 0. Okay, so we get an indeterminate form, and that kind of shows you that 0 over 0 and 1 over infinity, or 1 to the infinity, are both indeterminate forms when you're dealing with limits, right? So we can use L'Hopital's rule here, okay? And in doing that, we get the limit as x approaches infinity of taking the derivative of the top as a chain rule. Okay, so we're going to have 1 over 1 plus 1 over x. That will be times the derivative of the inside. Okay, now so you see how I have used, I've told you that you should memorize the derivative of 1 over x because it's negative 1 over x squared, right? And that's shown up like 2 times since I've said that, right? And it's about to show up again in the denominator. It's a really, really common derivative to have to take, so that's why I'm saying to, keep a mental note of it. The derivative of this 1 plus 1 over x is negative 1 over x squared. And then the derivative of the bottom, 1 over x, is, again, negative 1 over x squared, which cancels, okay? And you just end up with the limit as x approaches infinity of 1 over 1 plus 1 over x. Okay? So plugging in your limit, and you can't like plug in infinity, right? Infinity is a concept, right? Not a number, but I'm still going to, say that, okay, 1 over infinity is 0, okay? Because that makes sense to you. We can communicate that, and you understand what it means, right? So this ends up equaling 1. But that's not our answer. The reason why it's not our answer is because, well, you know that we didn't say that L was equal to the limit that we have now. It was natural log of L, right? We had to take a natural log of both sides. So to be completely done with this problem, natural log of L equals 1. Natural log of what gives you 1? Well, that's actually where e comes from. Okay? So if we actually exponentiate both sides, you'll be able to see that. If you have e to the natural log of something, that just ends up being that something, so we get L equals e. Okay? L equals e to the 1. So that's e. So we get that this entire limit here, okay, this limit that you would assume would be, 1 to the infinity, that's 1, right? Well, no. This ends up being e. Okay? So really, really interesting how 1 to the infinity doesn't end up being 1 here, okay? So you understand how 1 to the infinity is now an indeterminate form, because we're not talking about 1 exactly, right? We're talking about things that are other than 1, like things that are very, very, very close to 1 that are approaching 1, but they're not exactly 1, okay? So that's why I think we use 1 to the infinity as an indeterminate form, just to kind of make that make sense. So now we're going to be on to optimization, all right? And we'll start off with the easiest of the 3 optimization problems that we're going to be doing. I wanted to make sure that you get some extra practice for optimization. We're going to start off with the question, what is the largest possible volume that a box can hold if it is made from 1,200 centimeters squared of material and has a square base and has an open top? Okay, so how do you start off an optimization problem? That's probably if you can start this problem, that's the hardest part, honestly. That's the hardest part of an optimization problem. What you need to realize, okay, is that for optimization problems in Calc 1, you start off with you have a main equation and you have a constraint equation, okay? The constraint equation makes this an optimization problem, okay, and not some geometry problem, okay? The constraint comes in from our 1,200 centimeters squared. So that's a restriction, right? We only have 1,200 centimeters squared to use, or else our answer would be an infinite volume, right? So what's our main equation? That's going to be the first thing we should write down. Okay? Our main equation is the volume of a box, okay? It's got a square base, so it's not a cube, right? But it does have a square base, so we can say, instead of saying length times width times height, the length equals the width, right? If you're talking about that being just the base. So we can actually say that this is side squared times h, okay? And what that does for us is it eliminates one of our variables that we have to use, okay? So we only are dealing with 2 separate variables right now, side squared and our height, right? So now we have to deal with our constraint equation. And our constraint is that our total area, is only 1,200 centimeters squared. Okay? Now, the problem with optimization, okay? This is the hardest part, I think, of optimization. So first off, I feel like it's, organizing the information that you're getting into the main equation and the constraint, that's not something that most people think of. So I think that makes it harder. But then figuring out how to incorporate your constraint into your main equation, that's the hardest part of optimization right there. Okay? How do you incorporate your restriction into the actual equation that you're going to be taking a derivative of? Here, it's that, well, what's the total area of this box? Okay, well, it's got an open top, so we can talk about the area of the base being side squared. And then the area of all the other sides, right, the 4 sides is going to be 4sh, right? 4 times the side length times the height. Okay, so now what we can do, how do we incorporate that constraint? Well, what we can do is solve for h. Okay, that's going to be the easiest variable to solve for here, because if we tried to solve for s, we would get a quadratic, right? Or we'd get something, it would just be something nasty, I guess. I don't even know what it would be, honestly, but yeah, if we set 1200 equal to s squared plus 4sh, and we solve for h, we get 1200 minus s squared, right? So we subtract s squared on both sides, and then we would have to divide by 4s on both sides. So we get the h is this. Now this is how we're going to incorporate our constraint into our main equation. Okay, so rewriting our volume equation, we get volume equals side squared times h, which is now 1200 minus s squared over 4s. Okay, so we can rewrite this as a 1200 s squared over 4s minus a s to the 4th over 4s, which we can then rewrite as 300 s minus a s cubed over 4. Okay, so now we have something that's going to be really nice to take a derivative of. Okay, and the reason why we're going to take a derivative of it is because we're trying to find that largest possible volume. Okay, we're trying to find that largest possible volume. So we're taking a derivative, we're setting it equal to 0, and then we're finding what values of s are going to make that 0. Okay, and then verify that it's a maximum, go from there. Okay, so taking a derivative, okay, so actually I'll denote this as v prime. Okay, we get 300 minus a 3s squared over 4. Okay, and if we set this equal to 0, we can add 3s squared over 4 on both sides, and then s squared will become, multiply the 4 over, we get 1200. We divide 1200 by 3, and we get 400. So we can see that s is going to be, technically it's plus or minus 20, but we know that it's not going to be a negative distance, it's going to be a positive distance, right? Because negative distance wouldn't make sense. So we get that our side length is 20. Okay, now we do have to verify that this is a maximum, but it is kind of obvious that it's a maximum, right? Because we're not going to look for the minimum possible volume with a maximum area of 1200 centimeters squared, because we don't have to use all that area. We could just make like the smallest box possible with, like, you know, like an infinitesimally small box with infinitesimal amount of that area, right? So that's not going to make sense. So we can do a quick sign chart just to verify that in case that was confusing for any of you. We can use, you know, something like 1, and we can use something like 25. Okay, and what you'll find is that, and I'm not gonna, well, I guess I can do it, I guess we'll have a v prime, okay, of 300 minus a 3 over 4 if we plug in 1, and well, that's obviously positive. And if we have 25 that we plug in, we'll have 300 minus 25 squared. It'll just be some huge number, okay, and then it's times 3 over 4. It'll just be something larger than, times something that's larger than 300, and we get negative. So yeah, it's a max. Okay, so that's the idea. I am going to delete this because I want to have space to talk about what we're going to be talking about next, and that's finding our h from our side. We know that our h equals 1200 minus s squared over 4s. We plug in the fact that s equals 20, and we get this guy right here, right? And then we just go, okay, 800 over 80, and we find that h is equal to 10. Okay? So we now know our h, right? And now that I think about it, I guess we didn't even need to find our h. We could have just found the volume and then called it good, because that was what the problem was asking for, the largest possible volume. But what I did want to show you, because we're going to have a problem later where we're finding dimensions of something, that's how you find the dimensions. You just plug back into your original equation. So in that case, it was where we had something with s's equal to h. Okay, we found the dimensions of this box. It's going to be a 20 by 20 on the base and then 10 on the top. And using that, we can just find the volume. We get a 20 squared times 10, and so we would end up getting 4,000, and we can write that as centimeters cubed. Okay, and that's the answer to your first optimization problem. Now let's move on to the second. Okay, and actually this is the dimensions problem I was talking about. Okay, so we want to find the dimensions of the rectangle of the largest area that can be inscribed inside of a circle of radius r. Okay, so now we're talking about, this is a very popular optimization problem, and it's one of the tougher optimization problems, is talking about something being inscribed of something else. Okay, so it's just it's in this circle, it's touching the circle at all four corners. Okay, and I think the drawing of this is actually pretty hard in and of itself, because you have to realize that, at one of these points where the rectangle touches, you can just draw a line to it and call that your radius of the circle. Okay, and that's how you can relate the circle and the rectangle together. Okay, now here, right, we're trying to find the dimensions of the rectangle of largest area. Okay, so the area of a rectangle, right, that's our main equation. Okay, we're finding the largest area of a rectangle. So if we're finding that's the equation that we're optimizing, right? So our main equation is simply that area equals length times width. Now here, just to make our lives a little bit easier, and you don't need to do this on a test or anything, but I'm just kind of showing you this to make our math going to be come out a little nicer. The area here is going to be 2w times 2l. But you'll see why I did that in a little bit. But our area ends up equaling 4 times wl. Okay, so that's our main equation. Now, our constraint equation, we got to come up with some kind of constraint to incorporate this radius, okay? Because that's the whole point. This rectangle is being inscribed by a circle of a fixed radius. That fixed radius is r. Okay, that's not going to change to meet the demands of the rectangle. That's a fixed circle enclosing this rectangle. And we're trying to find the maximum area that this rectangle could cover inside the circle. So what we're going to do, the only way that, I can think of to incorporate this would be to use Pythagorean theorem. And that's why I used 2w and 2l, because I'm going to use these distances here. This distance is L, this distance is W. And so our constraint equation is going to be that R squared equals L squared plus omega W squared. I almost said omega. That's the if you kind of write it like this, okay, a W like that, that's the Greek lowercase of omega, and we use that all the time in like physics and stuff, especially in physics 4 right now, which is like waves and oscillations. We're talking about like frequency, and it's annoying. It's not like this. It's worse than optimization. Okay, so if you're a physics major, watch out. But anyways, let's solve for either W or L here, and that's how we're going to incorporate R into our radius equation. Okay, incorporating the constraint into our main equation. Again, that's why this is probably the most difficult part of the problem. If we do that, we get W equals R squared minus L squared. w squared equals that, and then we square root both sides and get w equals the square root of r squared minus l squared. Okay, so we're going to just plug this thing into here, and then that's how we get our radius incorporated into the main equation. So area is going to equal 4L times the square root of r squared minus l squared. So now we're going to be taking a derivative of our area equation. Okay, now the big thing to note is that we have two variables in this equation, so how are we going to take a derivative of it? The thing about this problem, okay, is it gave you a radius of r. Okay, r is a fixed radius. R is going to be a constant. Okay, so technically it's a variable, right? But it's fixed. Okay, so that's a hard way. It's hard to explain it, right? But that is a you're going to be given a radius like, okay, 5 or 6 or 7, but we're trying to find the actual value of the length, right? And that'll be in terms of the radius. So what ends up happening when we solve this problem, we get the dimensions. L and W are going to be in terms of R, right? So it's going to be like 3R over R plus 2 or something like that. And so somebody will give us a radius of the circle that's going to be inscribing the rectangle, and we can say immediately what our length and width dimensions are going to be. Okay, so R is this fixed value, so the derivative of R is 0, it's a constant. Okay, so in that sense, so we're going to be taking a derivative here with respect to L. Okay, so if we were to write that, we could write that as like dA over dL, right? We're taking a derivative with respect to L. All right, so L is the value that could possibly change. R is fixed. Now we take a derivative of 4L to get 4, and then we take a derivative, well, we don't take a derivative, we just multiply by the radical, we leave it alone, and then what we do is leave 4L alone and take a derivative of this r squared minus L squared. So we have 4L, okay, and this is going to be times another derivative to remember, okay, so is the 1 over x derivative to remember. Also remember the derivative of rad x. That's the other derivative that I would say to remember, because it does pop up a lot, like in this case. We don't have the derivative of rad x, but we have a derivative of rad something, so you'll be, I mean, you can treat it, you have to do chain rule, you have to treat it as 1 over rad x, or sorry, to do chain rule, you have to treat it as if it was rad x. Okay, and then you multiply by the derivative of the inside. So we treat it like it's rad x, in which case the derivative is 1 over 2 rad x. Right, that's the derivative that you should remember. Doing that, we actually get 1 over 2, the square root of, instead of x, it's now going to be r squared minus L squared, we just multiply by the derivative of the inside. Remember, r is a constant, so the derivative of it is 0. The minus L squared, okay, the derivative of that is negative 2L, and that's what goes on the outside. So combining this all, making this a lot nicer, we get 4 the square root of r squared minus L squared, and we get well, first off, we have one negative here, so this will actually be minus. Okay, the 2's cancel, and so we get a minus 4L squared now, because we have 2 L's, we have an L here and an L here, and we get that this is over the square root of r squared minus L squared. Okay, so that's our whole derivative equation. Okay, so now we have to set it equal to 0. Okay, so now we have to solve for what our L is going to be in terms of r. This looks really, really messy right now, but we can make it a lot nicer by finding common denominators. Our common denominator would just be r squared minus L squared, right? So if we found common denominators of r squared minus L squared, right, the square root of that, we just multiply by that square root of r squared minus L squared on top and bottom, and so we would end up getting just 4 times r squared minus L squared on the top, right? Because when you multiply that radical by that same radical, you just get that value that was in the radical in the first place. So you get this, and this will be over the square root of r squared minus l squared. All right? So the denominator just goes away because you can multiply that away to 0 and it becomes 0, right? So you can multiply the denominator on both sides, and then you would just end up with 4 times r squared minus l squared minus 4l squared. Okay? And you can distribute that 4, and what you would end up getting is 4r squared. You get minus 4l squared, but since we already have a minus 4l squared on the outside, this will become minus 8l squared. And we can add the 8l squared to the other side and get 4r squared equal to 8l squared. And then we would just divide by 4 on each side, get r squared equals 2l squared, and square root on both sides. So we get that, no, we're not going to do that. We're going to divide by 2 on both sides because we're solving for L, not R. So we get that L squared equals R squared over 2. And then we take a square root of both sides. And we get that L equals, it equal plus or minus the square root of R squared over 2. But we know that we're dealing with positive lengths here, right? We don't have negative lengths. It doesn't make sense. So we get square root of R squared over 2, which we can write as r over the square root of 2. Okay, so there's your length. Okay, now what would your width be? Okay, what would your width be? Because we're finding the dimensions. We're not finding the total area, right? We're finding the dimensions to give us the largest area. Okay, but we could find what the area would be in terms of r as well. You know, that's just not what the problem is asking for. So we know that W equals the square root of r squared minus l squared. Okay, and using this equation, I'll actually put this up here, okay, to give us a little more space. So solving for W here, we get that r squared, we get the square root of r squared minus L is r over rad 2, and that gets squared. So what we get is W equals the square root of r squared minus a r squared over 2, which gives us the square root of r squared over 2. Right? Just do a little bit of common denominator subtraction there. You see square root of r squared over 2. Now that equals r over the square root of 2. Okay? And there's your length and your width. Okay? Now that makes sense though, that your length is equal to your width, because you get a square, and a square would fill up the maximum area inside that circle. Okay, so that's actually pretty interesting to see. Now wait a second, you're not done. The reason why you're not done is because that wasn't our original dimensions of our drawing, right? The original dimensions of our drawing was 2W and 2L. So we'll actually need to write what 2L and 2W are. That's why I saved some room at the bottom here. 2L will equal 2r over the square root of 2, right? So we'll just double the length. And we can actually write this as r rad 2, okay? Because basically what you have here is you have a 2 to the first power of r over 2 to the 1/2 power, and you can write that as 2 to the 1/2 power over r, or times r, which is rad 2r. Okay, so this is actually your length, and so it would make sense that your 2 times your width would give you your actual width, which is r rad 2 as well. Okay, so hopefully that makes sense. All we did to start off this problem is we used, we found what the main equation was, which that's the equation that we're optimizing, the area of a rectangle, right? Because we're trying to find the largest area of a rectangle. And our constraint equation will deal with our constraint, right? Which is where this circle is inscribing our rectangle, and it has a radius of r. Okay? Finding the constraint equation here was a little more difficult, right? But that's the only way that you could have really used your radius here, is to, well, have the Pythagorean theorem. So you use that, you solved for W in terms of R and L, and you just plug that into your area equation, right? And taking a derivative with respect to L, we were able to find L in terms of R, and then we've used that in the equation that we found right here, right, that we used when we solved the Pythagorean theorem for W, and we got what W was. Okay, so, and of course we had to remember to correct what our original length and width was, which is R rad 2. Okay, so, you know, it is a lengthy process. I don't know if you'll get an optimization problem that's that lengthy. You could, but, you know, keep in mind that would probably be like the only optimization problem that you get, right? So, but inscribed problems are very common. I just think if you got an inscription, I don't think that's the same thing. If you got a problem that was having you inscribe something and then finding the maximum area, it shouldn't be the hardest problem in the world. But that also depends on what kind of calculus program you're in. So the last optimization problem that we have is asking us to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. And we need to find what is the distance between those 2 points. Okay? So what's our main equation? Right? That's the first step of an optimization problem. What is our main equation? Okay? Well, we are trying to find the closest distance. Okay? Closest distance. So we're using a distance equation. The distance equation is that the distance between the distance from the origin to a point is the square root of x squared plus y squared, right? It's the Pythagorean theorem. Okay? So that's where the distance equation comes from. Okay? So what's our constraint? Well, first off, the main equation isn't done because we have to incorporate the point. Okay? So the point isn't our constraint equation, the point goes in our main equation. Okay? Because, like I said, that was the distance from the origin to a point. We're looking from, instead of the origin, we're talking about a point 1, 4 to a parabola. Okay? The parabola is our constraint equation, that y squared is equal to 2x. But how we incorporate the point in our main equation is by doing the square root of x minus 1 squared plus y minus 4 squared. Okay? So now, and I guess it would make sense to write it like this, right? You have to flip the signs when you do that, so it's minus. Okay? So now we have to figure out a way to incorporate our constraint equation in our main equation. And, well, we basically can just divide by 2 on each side for our constraint equation and get that x equals y squared over 2. And then we just plug that into our main equation, and then we can freely take our derivatives. Okay? So actually, that wasn't the hardest thing in the world. For the last problem, we have to figure out what our constraint equation is, and then we have to realize, okay, we can solve for one of our variables here. So it's not as bad as the last problem, okay? And hopefully it starts this whole process. Excuse me. This whole process starts to make a little more sense to you now. Okay? If x equals y squared over 2, then we plug into our main equation, and we get y squared over 2 minus 1 squared plus y minus 4 squared. Okay, and distributing that out, we get the square root of, and you know what? You know, we have this square root here, and it's kind of nasty to have to deal with all this. We don't have to include the square root. And here's why I'm saying that. Because it kind of makes sense that the minimum point at D would be the same place where a minimum occurs at D squared, when we're talking about the distance equation D squared. okay? If you square the d, right? If you square d, you just get this without the radical, right? So you just get this, okay? And what I'm saying is that you'll have a minimum occur at the same exact place, because if you're squaring everything, right, and the minimum point was 3, now it's 9, and everything gets squared, well, 9 will be our minimum, and that occurs in the same exact place, right? Does that make sense? Hopefully that makes sense. I can't see if you're shaking your head in disapproval, or if you're like, oh yeah, that's cool. So we're just going to use d squared now, okay? And we'll call that d. We'll call that big D, okay? And capital D, because I would rather not say big D, is equal to y to the 4th over 4 minus this will be a 2y squared over 2, so we'll write it as y squared, and then we'll have plus 1, and then we'll have plus y squared minus 8y plus 16. Combining like terms there, we get d equals y to the 4th over 4. The y squared terms go away, and we just get minus 8y plus 17. Taking a derivative of capital D with respect to y, we get a y to the 3rd. Could we get a 4y to the 4th over 4? We get a minus 8, and the 17 goes away. So there's your derivative. So now we set it equal to 0. We get 0 is equal to y cubed minus 8, and y cubed is now equal to 8. We take the cube root of both sides, and we get y is equal to 2. Okay, it's not going to be plus or minus 2. We're taking a cube root here, not a square root, not an even root. Okay, if it was an even root, we need a plus or minus. If it's an odd root, we don't. Okay, so we get y equals 2. Now we could just use that to find our x. Okay, so we use that to find our x. Now, if we plug that into our equation, right, which this is how we incorporated the constraint into our main equation, right? That's how we're going to find our other variable. X equals y squared over 2. It equals 2 squared over 2, and so x also equals 2. Okay, so x equals 2. So that right there is the point on the parabola where the shortest distance is from that point to the point 1,4. I said that kind of weird, so let me say it again. 2, 2 is the shortest, 2, 2 is the point on the parabola that's the shortest distance to the point 1,4. All right, that sounds a little bit better. So now we got to find that actual distance, right? And we're going to go back to using little d or lowercase d now, because we can't use the larger the capital D equation for it, because that was d squared, right? That was little d squared. So we have to write our original equation for d, and we plug in 2 minus 1 squared, and then we have a 2 minus 4 squared. So we get d is equal to the square root of 1 squared plus 2 squared, and we get d is equal to the square root of 5. So we have our distance, and we have our point, which is 2, 2, which we can also circle. Okay, so that's the idea with optimization problems. I just want to review real quick with you guys so you understand how to tackle a optimization problem. The first step, and you can write this down, the first step when you tackle an optimization problem is to write down your main equation. Okay, that's the first step, and that's the equation that you're trying to optimize. Find the maximum area. Okay, well now you're finding the area of whatever that shape is, a rectangle or something. That's your main equation. Okay, the equation that you're optimizing. The constraint equation is whatever your restriction is in the problem, right? In the first problem that we did for optimization, it was 1,200 centimeters squared, right? That was our total area, so we had to use a total area equation, and then we found a way to incorporate that constraint equation into the main equation. Okay, and that's the third step. And generally, either the second or the third step is the hardest, I usually think. Like, using, I would say the third step. Finding a way to incorporate the constraint equation into your main equation. If you can do that, then you're fine, right? You just then simplify, take a derivative, set that derivative equal to 0, find your critical points. Okay? And you probably have seen that I haven't really been verifying that these things are max or mins, and that's because generally it's kind of obvious if it's a max or a min. Okay, so it might be a little bad practice on my part, but I really want you to understand the meat of the material here, and hopefully you're able to do that. Okay, so one more time, you start off finding your main equation, you find your constraint equation, you incorporate your constraint into your main equation, and then you have that equation that you take a derivative of, right? So your main equation incorporated with your constraint equation is what you take a derivative of. You set it equal to 0, find the critical points, or, well, point, okay? And, well, then you have to go from there for whatever that problem is telling you to do, okay? So hopefully that makes sense, and that's how to tackle any optimization problem that you see. Moving on, we're now going to talk about integration. We're going to talk about the fundamental theorem of calculus, okay? And I'm going to talk about the part 1 first. Okay, you notice I don't have a problem here. The problem is below, but I want to go over the fundamental theorem of calculus first, because I think this is something I didn't fully understand, and I ended up I ended up being a little frustrated because I didn't understand the fundamental theorem of calculus fully, and so that led me to struggling a little bit. So what part 1 is saying is that if you have a function g of x, right, and it's equal to the integral from a to x of f of t dt, okay, then if you take a derivative of that function, you're taking a derivative of an integral, right? So it's kind of like doing the opposite. It's like plus 1 and minus 1. They come together to be 0, right? So they kind of cancel each other out. But that's not the full story, because how I like to put this is that g prime of x equals f of x, and that's usually what you see people leave it as, but I like to also incorporate f prime of x in there, because that's the full story. That's telling you everything. And the reason why we have the f prime of x there is a chain rule. If you're not understanding why we have a chain rule there, which, it took me a while to figure that out, even just reviewing this, I'll show you where the chain rule comes from in the problem that we're about to do. So, going to that, we're going to find the derivative of the function f of x equals the integral from 1 to e to the x of natural log of t dt. So where the problem arises here is that, well, you don't have an x as your upper bound, you have an e to the x. And if they gave you a problem like fundamental theorem of calculus part 1 on your final, I don't think they would have an x as your upper bound. I think they would have something other than an x. So you'd have to use the chain rule. And let me show you where the chain rule comes from. So let's let u equal e to the x, and this becomes a little more obvious. Okay, so we can rewrite this as y equals, and I'll write y instead of f of x, okay, because then we get a integral from 1 to the u of natural log of t dt. Okay, now what happens is, well, we'll have to take a derivative. We want to take a derivative on both sides, okay? Eventually we want to find dy dx, okay? So our goal is to find dy dx, okay? So we take a derivative on both sides. Now, we take a derivative with respect to x of y, right? That's how we get dy dx. But now we have to figure out how this works on the right-hand side, okay? And to do that, we set up a chain rule. And chain rule, I can express it with a formula before we actually end up doing anything. Okay, this comes about because, well, what you end up having is a dy over du, right? You start off by taking a derivative with respect to u of this, and, well, this piece was originally equal to y, and that's why we express it as dy du, right? This whole thing was originally y. Okay, but then to get this thing to be dy dx, you would have to multiply by du dx, because then the du's cancel out and you get dy dx, right? So you have to multiply this whole thing by du over dx. Okay? So that's how chain rule ends up incorporating in there, or how it ends up, showing up. Okay? And that happens whenever you go through and actually do a fundamental theorem of calculus problem with the part 1 version, but it's just not really, it's not noticeable because the derivative of x is 1, so you're always multiplying by 1 when you do it regularly with x as your upper bound. So you just got to remember to multiply by the derivative after you're done plugging in. That's what this means, okay? So let me go through and I'll show you what this notation is, because I know when I was in Calc 1, and I'm going to be honest with you guys, I saw the teacher do a bunch of notation and I got kind of like, I kind of got afraid. I was like, I don't know what all this notation means. So let me go through and just make sure you get what this ends up meaning, okay? We set y equal to the integral of 1 to the u of natural log of t dt, and through taking a derivative, well, we would get our dy du piece, which in this case will end up being, what color are we on? We're on blue, I think. Yeah. dy du ends up being just the derivative of this piece, right? With respect to u, which is just natural log of u, right? Because the integral goes away and you plug in u. So we first off get a natural log of u. But then we have this du dx. And what that means is we have to take a derivative of u with respect to x. Remember, u is e to the x, so du, right, over dx is e to the x dx. Okay? So, well, sorry, the dx I moved to the bottom on the other side. That's where this came from right here. Okay? So we just have to incorporate that e to the x. So our answer ends up being that dy dx equals e to the x natural log of u, but we got to plug in back what our u was, right? And our u was equal to e to the x. So our answer is e to the x times the natural log of e to the x. Okay? But we can even simplify this further, and that's because if you put the exponent out front of the natural log, you get x times e to the x. I'll put the x outside of the e to the x too. And this is just times the natural log of e. And we know the natural log of e is 1, so this just becomes x e to the x. And that's your final answer. Okay? So that's hopefully going to help you fully understand the fundamental theorem of calculus part 1. And of course, if you have any questions, leave them in the comments down below and I'll try to get to them. Okay, so moving on to the part 2 of the fundamental theorem of calculus. Now this I can also hopefully help make sense a little bit more than it may to you right now. If you integrate from a to b of f of x dx, okay, it's the same thing as saying the antiderivative function of when you plug in b minus the antiderivative function when you plug in a. Okay, so I can kind of describe this graphically, and the reason why is because the integral from a to b is supposed to give you the area right here, right? Well, with the antiderivative function f of b, right, when you plug in b to the antiderivative function, this is the area from 0 to b. Okay? And so you get this whole mess right here, not the area from a to b, but when you plug in a and you subtract it off of that, the reason why that works is because, well, that's the area from 0 to a, right? That's the area that you have to subtract from f of b. So you end up subtracting this piece right here. Okay? And so what you're left with is that just that area from a to b, and that's exactly what you want. Okay? So that's why the fundamental theorem of calculus part 2 makes sense. All right, so now let's go ahead and use it with this integral. Okay, this is the integral that I actually clued you on in earlier. The integral from 1 to 2 of x cubed plus 3x to the 6th all over x to the 4th dx. Okay, this integral and I said this is a story for the other time when I was in the, like, I don't know, we were on like question 6 or something like that. But I'll actually tell you what happened. I was on a calculus 2 test, and I had an integral like this, and I was just, trying to think of how on earth I could solve it. I think I did like partial fraction decomposition, which is, by the way, you don't know what that is yet, but it's awful. It's a very long process, and it takes like 10 minutes to do one problem. But anyways, how you could have like solved this problem, okay, is just by realizing that there's multiple terms in the numerator and there's only one term in the denominator, so you can just split your fraction up, okay? And it never occurred to me to do that, right? So it just becomes really nice because you only have one term in your denominator. So what you can do is just say that this is x cubed over x to the 4th plus 3x to the 6th over x to the 4th dx, right? And literally I could have done really well on this test, but I messed this up, and then I got points off and didn't get the score that I wanted to get. So just don't be like me, people. So you get when you simplify here, you get 1 over x plus 3x squared dx. Okay, and when you integrate this, because now we're in a good place to integrate. The integral of 1 over x is the natural log absolute value of x. Okay, make sure you include that absolute value. And then the integral of 3x squared. If you undo power rule, that's just going to be, well, I'll write it as, because you're probably a little new to integration at this point, it's 3x to the 3rd over 3. Right, so I keep that 3 on the outside, and then the power goes up, and that power that I just got goes to the bottom. Okay, so that's the reverse power rule. And then I evaluate this from 1 to 2. Okay, so that just means the evaluation bar, by the way, if you are a little confused on what that means, that just means now it's ready to do this step. Okay, so natural log of, you plug in, you have your f of b, right, which just means we're going to plug in 2 everywhere we see an x. Okay, so we get 3 times 2 cubed over 3. And then we have our f of a, which is just plugging in 1, right? We're subtracting the area, the unwanted area from 0 to a, so we can just get the area from a to b. So we get natural log absolute value of 1, which is just 1, plus 3 times 1 cubed over 3. And so this piece right here is 0. This piece is 1. Right here, this piece is 1. So we get a natural log of 2. I can, get rid of the absolute value signs now. We get plus 8, and then we have a minus 1, because there's a minus sign here. So we just get natural log of 2 plus 7. And that's our answer. Okay? Moving on, we're going to talk about indefinite integrals, and basically with indefinite integrals, you don't have bounds yet, or you don't have bounds. In indefinite integrals, you'll use them in certain cases, but no big deal. But I have a quick problem here for indefinite integrals. You have the integral of x squared plus 1 plus a 1 over x squared plus 1 dx, and all you got to remember for this, the hard part, we can integrate x squared, we can integrate 1, but you got to remember that this is arctan. Okay, so if we integrate x squared, we get x cubed over 3, right? So that 3 just comes down at the bottom here. You integrate 1 to get x, and you should know that the integral of 1 over x squared plus 1 is the inverse tangent of x. Okay, now make sure you know that integral in specific, because that's also something that messed me up when I was in Calc 2, is not knowing that integral by heart. And so that was another place where I got a problem wrong, because I couldn't finish it because I didn't know the integral of 1 over 1 plus x squared. Okay, and remember, for an indefinite integral, you need to have that plus c at the end. Okay, because plus a constant. If you were to take a derivative of this, okay, that constant would go away. So if we had, so this is the antiderivative, okay, so it's the antiderivative. So we kind of did a derivative backwards, right? So if you were to take a derivative of that and have any constant in for c, you're still going to get the same function that we took an integral of. That's why we have the plus c there, because the constant goes away. Moving on to U-substitutions. I want to explain U-subs to you because I think how a lot of people end up actually explaining U-substitutions is just by doing U-substitution and going, hey, look what we can do, and not really diving into what it actually is. So I want to kind of go over that quick, and that is basically that the U-substitution is a reverse chain rule. Okay, you're reversing chain rule. So if you have, for chain rule, talking about what chain rule actually is, you have the derivative with respect to x of f of g of x, right? That's the chain rule. And you know that that's the derivative of the outside, okay, treating g of x as if it was x. And then you multiply by g prime of x, right, the derivative of the inside. Well, how do we reverse something like that? Well, what we're going to do is let u equal g of x, and so du is g prime of x dx. Okay? Why that's nice is because when we do that substitution, we just get the integral of f of u du, which is something that's really nice. It's not this mess of notation. Okay? We just set g of x equal to u, and we set g prime of x dx, right? We just take a derivative of u, which would give us g prime of x dx, and we call that du. Okay? And that's what I said earlier. So, when I was doing, where is it? I was talking about when I did this thing right here. Okay? When you do u substitution, instead of having this be du over dx equals e to the x, we would write it as du equals e to the x dx. So we multiply by dx on both sides, because that's how you factor in for your integral, because you want du, right? In your integral, you have a dt, right? So you don't want du over dx, you want just du. Okay, you want the differential. And I think that is something that we did in the last video. Okay. So going back down to that. So yeah, we get the integral of f of u to u. Let's do a example. We have two examples for u substitution. One's with an indefinite integral, one's with a definite integral. Here we're doing an indefinite integral. We have the integral of tangent squared theta, secant squared theta, d theta. Okay? So now we got to find out, well, where is g of x and where is g prime of x dx going to come in? Okay, so we can actually make our substitution. Well, first off, it's kind of hard to see what our outside and inside functions are here, because we don't have a 2 theta here, but where that outside inside function's coming in is we have a tangent theta squared, right? So we have something being squared, and then we have a secant of theta being squared, right? And actually, I'm going to leave that as secant squared of theta, because that's, and we'll have a d theta here, because that's basically what we're doing here. Our g of x is going to be tangent theta, because the derivative of g of x is going to be secant squared of theta, d theta, right? So that's g prime of x dx. Okay, so putting that all together, right? And so you see where this notation kind of comes in. Putting that all together, if u equals tangent theta, and du would then equal secant squared theta d theta, right? When you take a derivative of tangent, you get secant squared theta. You move over to the d theta, and there you go. Okay, so you can just plug in. You get the integral of tangent is u, so then we have u squared, and then secant squared theta d theta is du. Okay, and then we just integrate that, and we know that's going to be u cubed over 3. Okay, and then we say plus c. But we're not done yet, because remember, with indefinite integrals, we want to substitute back in. Okay, so we want to find out what that, we want to, plug back in for what that value of u was in terms of x. So we write this as tangent cubed of theta over 3 plus c. And there you go. That's our answer. Okay, so it's evaluating, what's inside, getting all messed up, and then is there a g prime of x dx? Okay, that's what a u substitution happens, and you should be able to see when something like that is available. Now here's probably the hardest kind of U-substitution that there is. And that's why I wanted to talk about this. This is called I like to call this a reverse sub, okay? A reverse substitution. Because this is a little weird. And I definitely struggled with this when I was in Calc 1, so I want to talk about this a little bit, okay? You can see that our inside function is x minus 1, right? It's being taken to, it's a square root, right? So it's got a power on it, like tangent of theta had, right? It has that power of 2. Okay, this is a power of 1/2. That's the square root, right? But the derivative of this, right? Your g prime of x dx is just this dx, right? Because if you say u equals x minus 1, then du just equals dx. So how do we take care of this x that's sitting out here? Well, because I'll show this right now. If we plug in the everything right now that we have, we get x times rad u du. So we can't integrate because we have this x left out. How we do this is just by taking this u equation and solving for x. That's why I call it a reverse sub, because we're kind of like saying x equals instead of u equals, right? So we're saying x now equals u plus 1. And we plug that in. So we get now the integral of u plus 1 times rad u du. And you might be wondering, well, does that defeat the purpose of a substitution? Right? Because now we just have something else plus some, like something. So now we have a u plus 1, whereas before we had an x minus 1. The reason why this is better than before is because, well, now we don't have a square root of u of x minus 1. We have a square root of u. Okay? So we just have a u to the 1/2, and we can distribute that to what we have right here. You can see that we can distribute that square root of u. So we can get u to the 3/2 plus u to the 1/2 du. Okay? And that makes it really, really nice. Okay? And now we just got to figure out our bounds, remember, because our bounds are not going to be from 1 to 2 anymore. That's why I didn't put them in. When x equals 1, because that's our first bound right here, u equals, well, we just plug into this equation right here. U will equal 0. Okay, it'll equal 1 minus 1, that's 0. When x equals 2, u is going to equal 1. So those are our bounds. We have 0 and 1. Okay, so doing this integral, we have to say u to the 5/2, and we'll bring down that power in front, so it'll be 2 over 5. We have to flip it. So then we do plus, and it'll be u to the 3/2, and then we have to bring that down in the front. And then we just evaluate that from 0 to 1. In which case, it actually becomes really easy when you have a 0 in the lower bound and you have like a polynomial, because that'll just go away. It doesn't matter. And I'll show you why. You do a 2 times 1 to the 5/2 over 5 plus 2 times 1 to the 3/2 over 3 minus a 2 times 0 to the 5/2 over 5 plus 2 times 0 to the 3/2 over 3. And you can see that this whole thing is 0. Okay? And this just goes away because these are 1. So really you just have 2/5 plus 2/3, and that's it. And then you can just find common denominators here. You can go, okay, well, you multiply this thing by 3 over 3. This gives you a 6 over 15. Multiply this thing by 5 over 5, and gives you 10 over 15, and you end up getting 16 over 15. Okay? So that's the idea. With a reverse sub, this is, I think this is the hardest kind of U substitution you'll see, because it's kind of counterintuitive. It's not what you would think it would be. Like you go with your gut with what you think g of x is, which it would make sense because this is by itself, right? This is just alone, right? It doesn't make sense to have that as your u, right? This is your inside function. You set u equal to that, and then you use u to solve for x, and then you can plug in for what that x is right there. Okay, so I really hope that this video helped you. If you have any questions, you can leave that in the comments down below, and I'll try to get to them when I can. And I think that all in all, for your Calc 1 final, I think the big things to focus on are optimization, are, if you've done integration, I would focus on U-substitutions, because I think those are fairly new. You've probably just learned those, so going over that is huge. I think going over your derivative rules, making sure you're taking derivatives really well, and making sure you're able to apply them, okay? And if you're able to do that and you understand the limit stuff that we did, which, I think was the easiest part of Calc 1, then you should be all set for your final, okay? It's just, I think the big thing is making sure your derivative rules are crisp, making sure you understand optimization, and making sure, I think the other hard part is making sure integration is sound in your head, because you just learned that, okay? And you haven't really, had too much time to really process that information, because you probably just fit it in at the end of the semester or the year or whatever you're doing right now. So I really hope this video helped. Subscribe for for more content if you're taking Calc 2 especially. I'll have a final review video up on that. I do right now. And it would really mean a lot to me if everybody that watches this video ends up subscribing. I'll actually be able to hit 1,000 subscribers. So please help me get there. Anyways, yeah, that's gonna do it for this video, and I'll see you soon.